Hey Kelly, what you working on?
I'm trying to figure out the velocity coming out of an open container.
Are you getting anywhere?
No, I can't figure it out.
Hold on, let me help you. We're going to use a little something called Bernoulli's equation, but first we'll need this.
Listen up, girls, cause this is it. Bernoulli on the mic, teaching fluid mechanics. Use my equation and you will score. Passing fluids class, of that I'm sure. Use it for containers to find velocities. Pressure variation in string lines you'll see. Bernoulli is my name, fluids is my game. You know the protocol. Now it's your turn to ball.
Thanks, Bernoulli!
Now that Bernoulli has helped us find the correct equation to use, we are ready to begin solving our problem.
So pressure will be 0 at the top of our tank because it's open to the atmosphere. And it will also be 0 at point 2 because our hole is going to be open to the atmosphere as well. At the top, at point 1, our velocity is going to be 0, and we're going to solve for the velocity coming out of our tank. Z1 is going to be the 4 centimeters from the top of our water to the center of our hole, and Z2 is going to be our reference point at the center of our hole, which is 0. And then after solving our equation, we're going to get Z1 equals velocity squared over 2 times gravity, and that's going to give us a final velocity of 0.886 meters per second. As you can see here, the water is 4 centimeters above the hole that we have made. Okay, now we're going to solve for our volumetric flow. Since our velocity equals volumetric flow over area, we found our diameter using a precision measuring device and found that it was 20.69 millimeters. We then converted that to meters and put it in our equation. Our volumetric flow is then equal to 2.979 times 10 to the negative 4th meters cubed per second. Okay, now we're going to remove the duct tape to watch the velocity of the outlet flow. Now we are going to use Bernoulli's equation again to find the velocity and volumetric flow coming out of our second container, which has a Z1 value of 20 centimeters, while the diameter of our hole remains the same.
In this case, P1, B1, P2, and Z2 still go to 0, except Z1 will be 20 centimeters because the bottom hole is further away from the top of the water. And therefore we get, for our velocity, 1.98 meters per second.
So from the top of our water to the center of our hole is about 20 centimeters.
Okay, since velocity equals volumetric flow over area, we get for the volumetric flow 6.66 times 10 to the negative 4 meters cubed over seconds. Now we're going to show the 2 holes in one container, so the top hole will have a slower velocity than the bottom hole. Just a reminder that the top hole is 4 centimeters from the top of the water, and the bottom hole is 20 centimeters from the top of the water.
As you can see here, the velocity of the bottom hole is a lot faster than the velocity of the top hole. This is due to a higher pressure at the bottom of the tank. Just like in a swimming pool, the deeper you go, the more water pressure you feel above you.
Cause I slay, 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 I slay. We gon' slay, we slay, I slay, I slay. Okay, I slay. Okay, ladies, now let's get information.
I love the taste of blood.
Actually, now we're going to show the
for all people who don't know how to do math around here.
I told you I can't do this. I forgot what I was going to say.
What we're about to do is fill up our buckets with some water.
This conversation, always stay gracious. Best revenge is your paper.